Oh. All right, so we are in time. So let's start. Uh, in the last class, I talked about the balancing of chemical equation, and I told you at least there will be a one problem in exam to identify which one is balanced and which one is not balanced. All right. So then we started the equilibrium, and equilibrium is also important, and there will be one question in exam. Yeah. So let's talk about the equilibrium a little bit. So there are two kind of chemical reaction we have. One is a reversible, another is irreversible. So irreversible. So reversible means two ways. So it goes to the one way and it returns back to give the original thing. That's called the reversible. And irreversible is something it goes only one way and it doesn't return back. Yeah. So those kind of the reactions are called reversible and irreversible. So let's write one equation here. So here is a hydrogen and here is oxygen. So I give some fire here and I burn that one and I form water. So this is a one-way reaction. So it goes only one way. So if I mix hydrogen and oxygen and burn it, it becomes water. Water doesn't break to give hydrogen and oxygen. So this is not a reversible reaction. Everybody got that? So it's only one-way reaction. Yeah. But there are other kind of reaction like this one, N2 plus H2, and ammonia is formed. So you are combining nitrogen with hydrogen and you give ammonia. At the same time, when the ammonia start to form, it start to break. When ammonia forms, it start to break. Yeah. So it breaks and gives back to nitrogen and hydrogen. So this kind of reaction is called reversible reaction. Everybody got that? So if the length of this arrow and if the length of this arrow going this way and this way are like of equal length, this is called the equilibrium. Equilibrium means the speed of going to the product and speed of going to the reactant is same. So both ways speed is same. Make sense? It's just like if you take 1 hour from your home to here and you take 1 hour to go back to your home. So it's like the equal, right? So this condition is called equilibrium condition. But if this arrow is something like this, so let's say only like this. So this is not, this is reversible, but this is not equilibrium. So the rate of forward reaction is very big. So they are forming very fast, but this is breaking in this slow rate to give this one. Make sense? Everyone got that? Like that, yeah? So, so at the beginning, this happens. This is breaking slowly, but a situation comes. At that situation, the both way is becomes the same. Yeah. Everyone got that? So this condition is called equilibrium condition. So going front and going forward and going backward is called reversible. If the going speed of going forward and speed of going backward is equal, that is called equilibrium. Everyone got that? So this is not reversible. This guy is not reversible because there is only one way. So most of the reactions are like this. There are few reactions, they are like this. Yeah. So let's write one reaction here. So I have one reaction here in this. I'm in the lecture 2 slides of chapter 3, and I'm in slide number 7 here. So I have this compound here. So let's say slide number 8. So this is methane gas. It's like the gasoline we put in car, and then we burn this with the oxygen, and it gives carbon dioxide and water. Carbon dioxide and water. So this is the fuel, right? Fuel. So you burn the fuel and with oxygen, and you get carbon dioxide and water. Can you combine carbon dioxide and water to give back the fuel again? Impossible, right? If we can do that, we don't have to go to the gas station again to fuel the car, right? So you could just, you burn the fuel with oxygen and you drive your car. During the driving, you are producing this and this. Now, if you combine this and this easily and give back that CS4 and O2, you could just fill the car with that CS4 O2, and then you could drive again, and you don't have to go to fill the car, right? So this kind of the reaction is called only one-way reaction. So this is irreversible reaction, burning gasoline with oxygen. Everyone got that? Good. So, but this one, so this is a irreversible. This is irreversible reaction. So if the reaction is irreversible, there is no question of equilibrium, right? So equilibrium is for only reversible reaction. If the reaction is reversible and the rate of forward going and rate of backward going speed is same, that is called the equilibrium. Yeah. So this is irreversible reaction. So we don't have to worry about the equilibrium here. So let's look another reaction here. So this is CS3 COOS. So this is another compound. So this is called acetic acid. So this is basically the lemon or the vinegar. So if you eat pickle, like cucumber pickle, PICKE pickle. So the whatever you taste sour, 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 taste sour, right? So this is a vinegar. Have you got that? So this is called the weak acid. So you can eat this acid, yeah. So this is called acetic acid. So the acetic acid, if you put it in water, so put it in water. So put it in water. So this will start to break. So this guy start to break, and do I write water here? Yes, I write the water here. So it start to break right here. So acetic acid always break here. So CS3 COO, and then they break here. So that becomes CS3 COO, and this first part becomes here minus, and then the second part H is plus. So this H is going to combine with this H2O, and that forms S3O plus like this. So like that, yeah. So everybody got that? So I might have taught you, okay, the front is always plus, second is always minus. That's for the inorganic, but this kind of the organic acid, the H is always plus, yeah. CS3CO is minus and H is plus. So this is a vinegar. So let's say you have 1 liter of water. So you have plenty of water here, and you put 100 molecules of CS3COH. So 100, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So let's say you put 100 molecules of this guy in a lot of water. So there I have 100 of those ones there. Make sense? Out of those 100 particles here, out of this, at the beginning, I have 100. So I start, I have 100. So keep dissolving, or so they also call the ionization here. Allow them to break continuously. Meaning that put acetic acid in water and wait there for a while. Yeah, for a while. And if you count after some time, you will get here 99.5 of this is left behind, and about 0.5, 99.5, and then 0.5, right? So 0.5. So you see here, so out of 100 molecules of this one, about 99.5 is not broken, only 0.5 is broken. Make sense? Everybody got that? 99.5 means out of 100 particles there, 99.5 particles are not broken, only 0.5 particles are broken to give the product. Make sense? So maybe I can write a certain whole number. Maybe you are confused here. So let's say I would write at the beginning, I have 100 particles here. So I just put 100 particles in water. Let's say out of those 100 particles, only one particle break to give this one, and 99 particles are still in that condition. Make sense? So at the beginning, I have all this one. But after, let's say after 1 hour or maybe 10 minutes, whatever you measure, these particles, there are 99 of those particles are left behind. Make sense? So only one particle out of 100 particles is breaking. Make sense? So this kind of condition is called like this. So and I can write like this. So if you look here, so this is like that and like that. So this is called the weak electrolyte, and only one molecule out of 100 molecules is being broken there. Make sense? So this is also the reversible reaction, and it's in the equilibrium. Make sense? So it's impossible to break more than one molecule in this reaction all the time. So no matter how long you wait there, only one molecule break. Make sense? So keep waiting there, keep waiting there, keep waiting there. Only one molecule is being broken out of 100 molecules. Make sense? So just like I have 100 students here, no matter how many years I teach you, only one student pass. All other are left behind. Everybody got that? It's just like that. So this is called this is a reversible reaction. So reversible reaction, and this is also in equilibrium condition. So only out of 100, if you put 100 molecule here, out of this 100, one molecule is being broken, and 99 is always this one in this person. Good. Got it? So that's the difference between the reversibility and irreversible. But in case of that CH4 and O2, so I put a lot of CH4 and a lot of oxygen there, and I bond that one. All these CH4 are gone to give CO2 and water in this case. Yeah. So like that. So is there anybody? So people, still people are waiting. I don't know what happened here. Admit. I think I put a password there. So good. So already now here is a question: which of the following statement about the chemical equilibrium is not true? So there are a lot of true, but one is not true. So let's write one equation here. Which one is not true about this one? N2S2, I give NS3. So what is true and what is not true about this equation? At equilibrium, the rates of forward and the reverse reaction are equal. So how many are forming? That many are broken at that equilibrium. Make sense? So this is true. So if two people are coming in, two people are going out. Just like that. Yeah. So rate of forward reaction is rate of backward reaction. This is true. At equilibrium, the rate of forward reaction and reverse reaction are equal. Everybody got that? So this is true. That's the definition of the equilibrium. There is no observable change in a chemical system at equilibrium. I told you, if you have 100 molecules here, 100 molecules here, at equilibrium, you always get 99 here. So you try counting again and again and again in the system. Always you have a 99 particle of the acetic acid, and only one particle is being broken. So that's so in the total property is not being changed. Make sense? That one particle is breaking, and then that one particle is combining with another and going back, and at the same time another particle is combined as a breaking and going this way, and that another particle here is combining and going this way, and so the net property of that system is same. Make sense? So if here are 100 students, one guy is going out, so I become 99 here, another guy comes in, so I become 100 again, right? And another guy goes out, and we become 99 again. Another guy comes here and becomes 100 again. So the net at certain time when I'm measuring something, we always 100. Make sense? Like that. So there is no observable change in the system. If the system is in equilibrium, there is not. The change is happening, but I cannot see the change because one is going out, another is coming in. So we are always 100. Yeah. So this kind of condition is called dynamic equilibrium. Change is happening, but I cannot notice. Everybody got that? So like that. So in the third one, chemical reaction always proceed to our equilibrium. So if you start to do something, the system always go toward the equilibrium. For example, if I try to put it here, it's not in equilibrium. It's not in equilibrium. So now it fall down, now it's in the equilibrium. So any system always try to go toward the equilibrium so that it becomes stable. So this condition now is equilibrium, right? It's stable. So if I put this like this way, it may not be in equilibrium, but when it fall down, there is no way to further fall down. So this is the equilibrium condition. Make sense? So equilibrium is something, it happens continuously one direction and it reaches one place and there is no going further. So it can just go back, go front, go back, and it is in the equilibrium. Make sense? So like that. And what else here? All chemical reactions are product favored at equilibrium. So this means that all kind of chemical reactions are product favored. So what it is saying is that, so let's say I have CS3COOS here, and I am putting this guy in water, and CS3COO minus and H plus. So is it a product favor or reactant favor? Let's say, so I told you I start with 100 and only one molecule break to give this one, so I get 1 here. So let's say it's at the beginning it's 0 and I have 100 there, but after let's say 10 minutes or 20 minutes I have 99 of those here and only 1 in here, so I can never get more than 1 here. So this is a product favor or reactant favor? It's a reactant favor, right? So I only got to 1 product and 99 still is a reactant. Make sense? Everyone got that? So this kind of the reaction is called, this is a reactant favor because this reactant is not really being broken down to give a lot of product. Yeah. So this is a reactant favor. So this kind of reaction is reactant favor. Reactant favor. Because out of 100 product or the 100 particle of the reactant, 99 particle never react. They just stay like that. So that's called the reactant favor. Everybody got that? So like the pass favored or fail favor, right? So if nobody pass, so majority fail, meaning that failing favor. Yeah, just like that. Make sense? So let's write another reaction here. So let's write another reaction. So maybe, so let's write this one. I write another compound, ClCS3COOS. So let's write this one. So if I put this guy in water, let's say I have 100 particles of this guy. So out of 100, maybe 95 particles are broken. CS3COO minus and H plus. Look here. So I started with 100 particles here. So at the end of the reaction, or when the system reaches to the equilibrium, I have only about, let's say, 4 particles left behind there, and most of are gone here to give this 96. So this type of the equilibrium is called product favored equilibrium or product favored reaction. Make sense? If you got that? So all pass. So my students here are all kind of the product favored. Why? Everybody pass in this class. Make sense? So nobody is left behind. That kind of this is only 96% product favored here. So out of 100 particles, 96 particles of this break to give the product here. Only 4 particles didn't break here. Make sense? So this kind of the reaction is called a product favored because majority go toward product. Yeah. So all chemical reactions or the reversible reaction are not product favored. Some are reactant favored, some are a product favored. Make sense? So this reaction I told you is a product favored, but previous reaction when, sorry, this is CS2 here. So this reaction is CS2COH is product favored because 96% of this molecule break down to give the product, But previously I was writing this guy here, and I told you out of this 100, only one particle is being broken to give here. So 99 is left behind, and only one is breaking to give the product. Make sense? So this kind of reaction is called product favored, because majority of this, sorry, the reactant favored, majority of this reactant molecule didn't break. Everybody got that? So some reversible reaction are product favored because majority of them break or react. Some reversible reaction are reactant favored because majority of them they don't break or don't react. You got it? So that's the last is wrong. All chemical reactions are product favored at equilibrium. Not true. This is clearly not a product favor. Only one particle is breaking out of 100. So this is definitely not a product favor. Yes. I don't know. so because I didn't study, so I don't know. Yeah. So whatever you want to call. Yeah. Good. All right. So maybe there are very few molecules like that. Yeah. So therefore, there's no discussion in the book. Yeah. So all right. So now when we put chemical in water, so let's say this is water, and I put some chemical like the sodium chloride, right? So I throw there I have water, and I'm throwing there some salt here. So this is salt here. So so when you put this salt here and stir with a spoon, this guy is going to dissolve here, right? It just dissolves. Make sense? So something that dissolves is called a solute. Solute. Something that dissolves is called solute, because I put it here and I stir it. The sodium chloride is going to dissolve here, and you cannot see sodium chloride particle. That is called solute. So sodium chloride is solute. Make sense? So what's the definition of solute? Something you put in water and you stir with a spoon, and that substance dissolves. That is called solute. Yeah. And what is dissolving this sodium chloride here? We have water that is dissolving this sodium chloride. That water is called solvent. Solvent. So water is called solvent, and the salt or anything that is being dissolved in water is called solute. That's the definition. Everyone got that? Good. So something that dissolves in big amount of water or whatever, that's a solute, and water is solvent because water is dissolving the salt. Yes? Good. So what is aqueous solution? So another term here is aqueous solution. So I'm in 10th slide, aqueous solution, A-Q-U-E-O-U-S, aqueous solution. Aqueous solution. If I'm making the solution in water, that kind of solution is called aqueous solution. Make sense? So the solvent I'm using is water. So I'm throwing some of my salt. Maybe I want to throw lithium chloride salt here in water. So that kind of, and then I stir it, and lithium chloride dissolve it here, and that kind of the solution is called aqueous solution. Aqueous means in water. Make sense? Any solution that we make in water is called aqueous solution. Good. All right. So aqueous solution. All right. So I think everybody's in there. So when the solute and when the solute, that salt and solvent are there, and you cannot separate, you cannot see different in solute and solvent with your eyes. That kind of mixture is called a solution. Yeah, make sense? Solution. So, but if you see solid, so some solid here, that's not a solution. So water, and you see the solid two-phase. So that's not a solution. We should not be able to see with our eyes this this solid and this liquid separate. Make sense? So that kind of condition is called the solution. But if you see there is some solid and some liquid separately, that's not a solution. Got it? Yes. Look. Now, so what kind of substance dissolve in water? So this kind of substance dissolve in water. So ionic substance dissolve in water. Most of the ionic substance dissolve in water. Dissolve in water. So what is ionic substance? So ionic substance means take any metal and take any non-metal and combine them, and that is called the ionic substance. So take group 1 elements, so maybe lithium, sodium, and take any group 2 metal like calcium, magnesium, take any other developed element like iron, like copper, take any of these metals. So I told you all those blue elements in our periodic table in our book are metals, right? Take those metals and combine those guys with the non-metals. Maybe there is oxygen, maybe there is chlorine. So this is non-metal. This is also non-metal. Maybe this is fluorine, non-metal. So maybe you can put iodine here, non-metal. Maybe here you put oxygen. Maybe here you put maybe bromine, like this. You see that? So this kind of the material are called the ionic material. Make sense? So one is a metal and one is non-metal. So look here, all those these are metals. So look there, all those black elements there in the periodic table are metals. So all those, so the hydrogen is non-metal, all these are metals, and all these are metal, and this boron, carbon are not metals, but aluminum, gallium, these are all metals here, but these red are all non-metals. Make sense? All those black element, most of these elements here. So but in our book they are showing with the blue element there, blue color. So most of these elements here and like this, these are metals, and those metals combining with non-metals, those red element there are called the ionic material. Make sense? Everybody got that? So if you look your book, so there are all non-metal are orange, all metals are blue, yeah, and then metalloids are in green color. So if you put those blue together with the orange, and then you form the material that is called ionic compound. Make sense? So ionic compound are dissolved in water. So if you write here, so we write MgLiO2, NaCl, CaF2, MgI2, Fe2O3, CuBr2, like that, right? So I told you how to write those chemicals there. So this kind of the material are dissolved in water. So let's take in one example and see how this water dissolve NaCl. So NaCl is a table salt that we eat in our kitchen, right? So that's a table salt. How does this NaCl is dissolved by water? So you put the NaCl in water. So this is our water here. So Na has a plus charge and Cl has minus charge, like that, right? So this is the ionic compound. So Na has a plus 1 because there is 1. So that one is plus 1, and then there is minus 1. So we don't write 1 there. So when you put in the water, so this is NaCl. So the water molecule look like this: O, H, H. So this is water, and then this oxygen is has slightly minus charge. This hydrogen has slightly plus charge. So this is water molecule, one particle of water. Make sense? Everybody got that? So when I put this sodium chloride in water, what happens is sodium is here and chlorine is here. This oxygen of water is going to pull toward the sodium, like that, like this. You see that? So that there is hydrogen, there is hydrogen, there are 2 hydrogen here, there are 2 hydrogen here, there are 2 hydrogen here. So hydrogen, 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 like that. You see that? The positive sodium plus is being surrounded by negative O of the water. So this is negative. Oxygen is negative, like that. Make sense? Everybody got that? What I'm doing here? So because Na plus of sodium is being surrounded by the O minus of the water. Yeah. And then this Cl minus is being surrounded by H plus of that water. You see that? H plus. So toward Cl minus, H plus is surrounding that Cl. So what happens here is there was some force between Na plus and Cl minus at the beginning here. Now that force is being diluted by this O between the O and this H is between this sodium and chlorine. So when that force of attraction between sodium and chlorine becomes small, they are going to separate, and that's called dissolution. So that's how the salt dissolves in water. Everybody got that? So there are 2 good friends here. There are very good friends. So this is one guy. There is another guy. These are very good friends here. So they are happy and they are just sitting together, right? But their third person comes here and start to break the force between them, and this guy goes this way, this guy goes this way, and they get separated. That is called dissolution. Everyone got that? So that's how the ionic compound dissolve, and we will do in lab number 4 also. Yeah, and when we go to the lab in lab number 4, this is taught there. You got it? So how does the salt dissolve in water? So water is like this. The oxygen has negative charge, hydrogen has positive charge, hydrogen has positive charge. This is the salt. The salt sodium has plus charge, chlorine has negative charge. As we throw the sodium chloride in water, the sodium is being surrounded by the negatively charged oxygen of water, and chlorine is being surrounded by positively charged H plus of water. So the force of attraction between sodium and chlorine becomes very small. It becomes very weak. So NaNCl gets separated and they go away from each other. That is called dissolution. Everyone got that? So you will see this concept in lab number 4 too. Yeah, good. So I write there, so you can just read yourself. So now we talk about the electrolytes. So I'm in the slide number 11 of so what is electrolyte? So electrolyte. So if you buy some water bottle, they say outside, oh, this is a bottle of the electrolyte, right? There is electrolyte. So basically they are putting some salt there, maybe some sodium chloride, lithium chloride, some other kind of the salt. They are putting those salt, and those salt in water solution is called the electrolyte. Make sense? So what is electrolyte? So basically here we are defining electrolyte as we have water here. So this is water. So water, and we put some salt here. We put some salt like sodium chloride here. We throw salt here, and when I throw salt there, that becomes Na plus and Cl minus, NaNCl minus. So some becomes Na plus and another becomes Cl minus, like that. And if I put 2 electrode here, so let's say this is a copper piece, this is another copper piece here, and I connect it to the plug here. The plug here, like that. So the plug, the valve. You have a plug here, and you put a bulb, electric bulb here. So it gives light. So like this. This is called electrolyte. Make sense? So, but if you don't put water here, sorry, the sodium chloride here, it doesn't conduct electricity. It doesn't give the light. Everyone got that? So basically, electrolyte is a water and salt mixture that conducts electricity. And if you do this experiment, the light gives the bulb gives the light. Yeah, it's the mixture of water or the solution of water and some salt. That solution conducts the electricity. Make sense? So, for example, if you do this experiment, basically this is a plug, or you can say it's a battery. So you can put a battery here. So this is battery here. They say this is a negative pole. So this is a positive pole. So look here, what I did, what I put here, I put some water and I put some salt, and I stir with the spoon, and I put the battery here, and I connect the light bulb here. Did it give the light? Yes, it gives the light. So this mixture I have is the electrolyte. Everyone got that? Yes. If they dissolve, but there are some ionic compounds, they don't dissolve in water. I will talk later. Yeah. Good question. Yeah. Everyone got that? So like this. So what is electrolyte? So basically, electrolyte is a solution of water and salt or any other compound. The solution or mixture, right? Like that. Solution of water and salt, and this solution conduct electricity. If it conducts electricity, that is electrolyte. If it does not conduct electricity, that is not electrolyte. Make sense? Conduct electricity means that bulb give the light. Doesn't conduct electricity means that did not give the light. Everyone got that? So this is called electrolyte. So electrolyte is something, the solution of water in some salt, and that solution conduct the electricity. This is called electrolyte. So if I put the sodium chloride, like the ionic compound in water, sodium chloride and water mixture. So this is a electrolyte. It conducts the electricity. So if you put this in water, so it's basically Na plus and Cl minus. They are free here in water. So Aq means it's in water. Aq means it's water. So the solution. So if you have a water here, you put water here and throw some sodium chloride there, and it exists. The sodium and chlorine are separate, and put two electrodes here. One electrode like a copper piece, another copper piece here, and take a battery here and connect this to the minus. This a plus and minus pole with this one, and maybe you want to connect one bulb here, and then you get the light. Good. So this is called electrolyte, sodium chloride electrolyte. How about another one? So we have all kinds of all ionic compounds that are soluble in water are electrolyte. All ionic compound means those blue elements combining with the orange element of our book, are most of them are soluble in water, and they conduct the electricity, and they are electrolyte. Make sense? But if they don't dissolve, they are not electrolyte. Yes? Good. Metal. Good. Now, there are two kinds of the electrolyte. One is a strong electrolyte, another is weak electrolyte. So, strong electrolyte, strong electrolyte, a weak electrolyte. So, weak electrolyte. So, strong electrolyte is like this. So, put like 100 particles of sodium chloride there in water, 100 particles of sodium chloride in water, all sodium chloride break to give sodium and chlorine minus. Look here, 100 particles, 100 particles. So this is strong electrolyte. And if you do that light experiment, you see the very bright light in that ball. Make sense? All the particles of that sodium, the sodium chloride break to give Na plus and Cl minus. Yeah. So that kind of the electrolyte is called strong electrolyte. Make sense? Good. How about weak electrolyte? Again, now look here, CS3, COOH. I already told you. So this, if I put this in water, so out of 100 particles here, if you start with 100 particles here, only one particle is this one is being formed, right? 99 particle is still not broken. So this kind of the electrolyte is called a weak electrolyte. Everybody got that? So if you do the experiment with this one, so take water here and put this 100 particle of this CS3COH here, and do that experiment with the battery, minus, and this is plus and this is minus, put two electrode here, and then connect it here, and connect it here like that, and put a bulb here, and very dim light. You will see dim light here with this one. You got it? But if you do this experiment with the sodium chloride, you will see very bright light. Yeah? Because I put some 100 particles of sodium chloride in water, all 100 particles break to give the Na plus and Cl minus. So there are a lot of particles to do work for us. Yeah. So they are conducting the electricity. But if I do the same experiment with the CS3COH, only one guy goes for working, 99 particles are not working for us. Make sense? Because only one guy break to give some ions and conduct electricity. You got it? The strong electrolyte is all salt particles break to give ions, and they conduct electricity very strongly. And if we do the light experiment, the bulb gives very bright light. So that kind of the electrolytes are called strong electrolyte. But this kind of CS3COS, this kind of the electrolyte are called weak electrolyte, because out of 100 CS3COS particle, only one particle breaks to give some ion, and that conduct the electricity very weakly. And if you see, if I do the light experiment connecting with the battery, the bulb gives a very dim light. Yeah. So that's the difference between strong electrolyte and weak electrolyte. Have you got that? So we will do this experiment in lab number 4. All right. So how to identify if there are some something is electrolyte or not electrolyte? I told you strong electrolyte. You know now weak electrolyte. You know. So I'm going to put 4 compounds here and tell you or ask you if something is electrolyte, or they conduct electricity or not, they break into ions or not. So let's look at those. So as I told you, you take the metal, that's a metal, right? The group 1. So group 1 is here. So group 1 is here. So sodium is a metal, and you combine that with any non-metal here, maybe oxygen, fluorine, sulfur, chlorine, bromine, where you are combining. So Na2O. So this guy is a ionic material, right? Because this is metal, blue element, this oxygen is orange element, and metal and non-metal. If you throw this sodium oxide in water, it's going to give Na and OH minus ion, and it's a electrolyte. Make sense? If you got that? So like that. How about there is no metal. So if you have a metal and non-metal, you can easily identify, oh, something is electrolyte or not, right? So metal and non-metal sitting there, throw in water, they give ions, so they conduct electricity. That's an electrolyte. But how about if there are non-metals? Let's write non-metal. So this is carbon. Carbon is a non-metal. Look here, that's a red element there. In our book, that's an orange element, right? The carbon is a non-metal there. Yeah. So carbon is a non-metal. So let's look here, oxygen. So oxygen. So CO2. So this is non-metal. Is it an electrolyte or not electrolyte? It's a not electrolyte. Make sense? CO2 is not electrolyte. Maybe if CO2 is dissolved very high, it gives a little bit of carbonic acid, maybe in that condition, but most of the time in like CO2 is not electrolyte. Make sense? Non-metal sitting with non-metal. How about this guy? Cl4, the carbon tetrachloride. Is it a electrolyte or non-electrolyte? Will it conduct electricity or not? So non-metal. It's a non-electrolyte. It doesn't conduct electricity. If I throw this in water, it doesn't break to give that plus, minus, and it cannot conduct electricity. Non-metal. Make sense? So how about this guy? Let's try this one. CH4. So this guy, is this a electrolyte or non-electrolyte? Look here, non-metal. It doesn't break. Everybody got that? When there is a non-metal, it doesn't break and it doesn't conduct electricity. So this is non-electrolyte. You got it? So let's look another one. Is it but if you have H is a non-metal, right? H. So H is a non-metal. If you look there, H is non-metal. But if it is with a Cl, it becomes electrolyte. HCl, HBr, HI. So these are electrolyte. Although these are non-metal. This is acid. So acid is a electrolyte. Have you got that? If there is a H and that H is sitting with Cl, Br, and I, these are electrolyte. Yeah. See, HCl, but not CCl. So these are electrolyte. These are acid. We will talk later about the acid. And there is one condition here. So if you see something like this, COOH, something like this, this is an electrolyte. You get a compound and you see something like this. That is electrolyte and weak electrolyte. I already told you CS3, COOH, or any kind of thing, right? But if you see other kind of condition like COH, only OH, you see COH. So these are non-electrolyte. But if there are double OH, these compounds are electrolyte. They break in water, like acetic acid, propionic acid. So those are acid, yeah? COOH. So only one condition, like the organic compound, they are acidic COOH. So let's write one compound here, CS3 COOH. So I write like this. It's a electrolyte. I can write another like this, CS3 CH2 COOH. Electrolyte. I can write another one, CS3. I could write another one and another one. As long as I see COOH there, these are all electrolyte, ionic compounds, but weak electrolyte. Out of 100 particles of this material, only one particle break, and that conduct electricity a little bit. Yeah. If there is a COOH, these are the organic acid, and they conduct electricity, and they are called the electrolyte. Yeah, but it's weak electrolyte. They conduct electricity a tiny bit, and the bulb gives a dim light. Got it? Like, good. And I told you that HCl, H sitting with any of those polyatomic ion, or like HCl, HBr, HI, H2SO4, H3PO4. So you see here the polyatomic ion. This is the group 7. So these all are electrolytes. This hydrogen sitting with the polyatomic ion. So polyatomic ion means so this guy here. So a lot of polyatomic ion in this chapter 2, I write there nitrate, like NO3 is here. So NO3 is a polyatomic ion. So that's you put FNO3. So this kind of material are all acid and they conduct electricity. Everybody got that? H sitting with these polyatomic ions, H sitting with Cl, Br, I, they are acid and they are a very good conductor of the electricity and they are electrolyte. Yeah. And the organic compound, that's a non-metal sitting with only with this kind of condition, COOH, they conduct electricity. But other case like CCl4, no, it doesn't conduct electricity. Ci4, no, so it doesn't conduct electricity. Yeah, everyone got that? So look that COOH, and then this should be good. Now let's write one compound here, glucose. So glucose is like that. So I'm going to write glucose here. Does glucose conduct electricity? C6H12O6. You see that CHO? There is no condition like COOH. So this kind of condition, there is no that kind of condition. So this is not electrolyte, glucose. Yeah. So another one, let's write the alcohol, CH3, CH2OH. So this is the alcohol that we drink. Also, this compound doesn't have OOH type condition. So this is also a non-electrolyte that doesn't conduct electricity. Yeah. So you need to look OOH. Yeah, COOH. Everyone got that? So like that. So let's put the 3 here. So we all already talk a lot about the electrolyte and non-electrolyte. So electrolyte dissolve in water to give ions. They conduct electricity. A weak electrolyte, very few ions there. Give the dim light if I do the battery and that experiment, right? And the strong electrolyte dissolve all in water, break all the molecules in water 100%, right? And there are a lot of ions and they conduct a lot of electricity and they give the very bright light in that battery bulb experiment, right? So strong and weak. So like that. And non-electrolyte, they don't break into ions, like they don't give plus charge and minus charge. They don't conduct electricity. Now conductivity. So here is the in this slide that experiment I already explained is here in that slide number 3. So basically they are showing the same thing. So if you look there, so they have 3 things here. So 1, 2, they are doing 3 experiments here, and they have some salt water or whatever water here, and they are putting a battery here. Plus one side is a plus minus, and they are connecting this here, and on this side they are connecting here in another one, and they are showing a lot of very bright light here, very bright light here. So if there is a very bright light, this solution is a very strong electrolyte. Make sense? So here in the another one, they are doing the same thing. Put battery here, plus minus here, and put here like that, and like this here, and there is some water and whatever mixture is here. This bulb is giving dim light, slight amount of light here, right? So this is conducting electricity very weakly. So this is a weak electrolyte. Make sense? And the last one, they are doing the same thing here. Put battery here, the plus pole of the battery, minus pole of the battery, connect it here in the water, and then put here in the bulb here, and then put it like that. And here is water and whatever the mixer, and this is not giving any light. So this mixer is non-electrolyte. Everybody got that? Easy. Yeah. That experiment, bright light meaning that solution is strong electrolyte. In this experiment, dim light means that this solution is weak electrolyte. In this experiment, there is water and it's not connecting to the battery. This is not giving any light, meaning that this is non-electrolyte. Yeah, that's how we identify if something is electrolyte or not. Everyone got that? That's the experiment. Yeah. So strong electrolyte, weak electrolyte. I already told you how to identify. Let's. There are some example in slide number 4. That's slide number 4. So I'm writing 2 example here, like CS3 COOH. Is it an electrolyte or not electrolyte? It's an electrolyte. There is this condition COOH. Yeah, and I told you it's sitting with Cl, it's sitting with whatever I, Br, that's always electrolyte, right? and H sitting with the polyatomic ions, HNO3, H2SO4, S3PO4, whatever. They all are electrolyte, yeah. And then like this compound, CS4. Is CS4 electrolyte or no? So non-metal, non-metal. So non-electrolyte, yeah. So C2H6, both non-metal, like that, yeah. Everyone got that? So there are few examples. You can just read yourself and got it, right? So the base and acid, if there is a H with Cl, like HCl, HBr, HI, H with a polyatomic ion, HNO3, H2SO4, S3PO4, those are all called acid, and all acid are electrolyte, yeah? Have you got that? Good. So how much time we have here? Still we have some time here. So reaction in aqueous solution. So most of the chemistry in chemistry laboratory is done in water. So some of the reaction is done in some organic compound like acetic acid or whatever other organic like ethanol, methanol, right? There, but most of the reaction in chemistry laboratory is done in water. So you take water here, and whatever reaction you want to do, just throw it here. So maybe you want to react with water and sodium, or maybe you want to react sodium and other material there. So throw there and they will react like that, yeah? So reaction in water is a medium. So if there are two things and they are in the solid, although they come in contact, they really don't work well. So we need to throw them in water and mix them, yeah? So water is the medium. Have you got that? So water is the medium. So so what is the difference between molecules and ions? So let's say, so Na plus Cl minus, this type of condition is called the ions. So the particle has plus charge and particle has negative charge, either plus or a negative charge. This kind of particles is called the ions. Have you got that? So the molecules, so let's say CCl4. So this does not have any plus or minus charge. No plus or minus. So this is called molecules, and this kind of condition is called ions. Make sense? So the difference between ions and molecules. Ions have plus and minus charge. Molecule don't have charge. Everyone got that? So this guy doesn't have any charge. So if you put this guy in here, CCl4 here, and put connect it with the battery here like that. So like this. So this molecule, if you put this molecule CCl4 right here, it doesn't move this way. It doesn't move this way. So this guy doesn't have charge. Just sit between. Make sense? So this is a plus. This is a minus pole. And if I don't have charge, I just sit like this in the between like that. I don't move this way or I don't move this way. Make sense? But if I have charge like the Na plus or Cl minus, either I move this way and sit like that, or either I move this way or sit like that. Have you got that? Good. So this guy is a molecule. It doesn't have charge. So if you put here, it doesn't move this way. It doesn't move this way. But if you put sodium and chlorine here, sodium is here. So this is a plus here. So this guy is a plus. Since sodium is plus, it goes toward, this is minus. Sodium would go toward minus, and it's a chlorine. Chlorine would go toward plus, like that. Yeah. Plus goes toward minus. Minus goes toward plus. Have you got that? Now, so if we do reaction, what happens? So let's say if we do some reaction, from a reaction, what forms? So let's say if I Ag silver nitrate is here and I have a NaCl here. So what happens if I do this kind of the reaction? So what happens? So I have a solution of so I have water here and I have this AgNO3 dissolved here, right? And then I have in this one, I have some water here and NaCl is dissolved here. NaCl is dissolved here, AgNO3 is dissolved here. So I have two things there. This is that's a AgNO3 solution. This is NaCl solution. So if I react, what happens? There is nothing here. I cannot see this AgNO3 with my eyes. If there is NaCl, I cannot see with eyes because it's a solution. Now, if I mix these two together, I get a lot of white solid here, white solid here. So this is called precipitation. Make sense? So sometimes if I mix the two chemicals together in water, they give new solid, new precipitation. Make sense? So that's like that. And the second one, sometimes it gives gas. So let's write another here. So let's write the calcium carbonate. So you have a calcium carbonate and you put some HCl in water. So meaning that you take a beaker here, and then you have some water here and some HCl, put some HCl here and throw some calcium carbonate, and you see a lot of gas coming out. Carbon dioxide gas comes out, just like you open the Coca-Cola bottle and the gas comes out, right? Just like that, you see that kind of reaction. So in chemical reaction, sometimes you see the gas. Yeah, sometimes you see the white precipitate down there, solid. Sometimes you see the gas coming out from the reaction, and sometimes weak electrolyte form. So weak electrolyte form meaning that, just give one example. So let's say HCl. So if you have HCl, this is very strong electrolyte. Hydrogen sitting with this chlorine is a very strong electrolyte. Yeah, I already told you. Hydrogen sitting with chlorine, hydrogen sitting with bromine, hydrogen sitting with iodine, or hydrogen sitting with the polyatomic ions. Those molecules NO3, S2, SO4. Those are very strong electrolyte. Now you mix this with another guy, NaOH, like that. NaOH. This is also very strong. This is a base. So if you combine this one, so this guy and this guy sit together, and this guy and this guy sit together, H2O. So look here, H and OH sitting together is H2O. So this is a weak electrolyte. It's basically H2O is a non-electrolyte, but sometimes water is considered as a weak electrolyte. Yeah, sometimes they give weak electrolyte like this. Weak electrolyte. Water is weak electrolyte. It's pretty much it's a non-electrolyte. Water is non-electrolyte, but if you really study in depth, sometimes water behaves as a weak electrolyte. Yeah, so like that. So sometimes if you mix a very strong electrolyte, this is very strong, this guy is very strong. Now you produce the water. Water is a very weak electrolyte. Sometimes in chemistry, non-electrolyte like water, these are the treated as a very weak electrolyte. Yeah. So out of 10 to the power minus 7, I think 1 molecules of water break out, something like that. So 10 to the power minus, out of 10 to the power 7 molecules of water, 1 molecules of water break to give H and OH. Yeah, so that's a very weak electrolyte. 10 to the power 7 is millions out of millions of water molecule, 1 molecule break to give the H. So very weak electrolyte. Yeah, that 10 to the power 7 is a very important number for water. Yeah, so that's we call the pH of water is a 7. So already, so like that. So sometimes weak electrolyte is formed. So in this case, what we studied is sometimes 2 material are mixed together and we see the solid, and sometimes we mix 2 material in water and we see the gas coming out, and sometimes we mix the 2 strong electrolyte NaOH and HCl and we form the water, which is a weak electrolyte. Yeah. So those kind of the material we form. So here is a important, not that important, but it's a solubility test. So I give you some compound. So in the laboratory, you have this bottle. So you go to the laboratory and you find a bottle of, let's say, copper sulfate. So copper sulfate is written in this label. So there is a label, copper sulfate is written in this label, right? Does this, if you, so there is a water. Now you are predicting, I want to put a little bit of copper sulfate from there to here in water. Does that dissolve here or does not dissolve? Yeah, without doing experiment, we need to, we try to know. If you got that, what I'm trying to say. So if you take some copper sulfate here and you put it here and stir it, you immediately know it dissolves, right? All copper sulfate you put is gone, right? But we are not doing any experiment, and we just want to predict it by just looking the chart. Yeah. So does copper sulfate dissolve in water or not? So they're not that chart. I'm not looking this chart. I put this chart in the so let's see here. I put here. So I will show you. This is a lecture 3. So this one, I'm talking about this one. So let's practice couple of things. So if you, I don't know if the online, the people in Zoom can see that or not. I am talking about this slide here. I will show you. So you will see this kind of the slide here. So I'm showing here this slide. You can go there and look there. So there are some red and green letters there. So I'm just talking about that. Yeah. So look there. So let's practice some fault whether they dissolve or not dissolve. Look here. I'm going to put NS4 and F here together in the board, NS4 and F, right? So just like the multiplication table. So I'm going to put NS4 and F there. So NS4, and so up there is NS4. Here is a NS4, and I come from here and I'm putting NS4 and F together there. So NS4 is +1 and F is -1 there. So if I pull this one down here, I don't have to write that one. I pull this one here, I don't have to write this one. NS4, right? So look just below that, and NS4. Just looking here, NS4F. This compound is soluble in water. All those green boxes means that those are forming those compounds are soluble. If you got that, NS4F is soluble. So without doing experiment, I found that NS4F is soluble in water. Yeah. If you got that, so you'll see some question in exam. So you can use this chart and you can predict whether some compound are water soluble or not. So let's practice another one. So let's take one red button from here. So I'm going to take this button here, INSOL, insoluble here. I go up here is magnesium, Mg2 plus, right? Mg2 plus, and down here is this guy. So from S, so I'm just looking here. There is a S here, S2 minus, right? So from here, from Mg, I go down here, and from here, am I doing this one? Or maybe I'm looking OH here, Mg and OH, right? Mg and OH. So that's Mg, and I'm looking OH minus here, like that. Have you got that? Just like the multiply. So maybe you already know the T, like you know the multiply table. So we do like this. So multiply table is like this, right? We do like that. So 1, 2, 3, 4. 1, 2, 3, 4, and 2 multiplied by 2 is what? So I go this way, and this way 2 multiplied by 2 is 4. So 2 multiplied by 3 is what? 6. So we practice like that way, right? I'm just like doing that, yeah? Have you got that? Like this. So Mg2OH. So this 2 should be coming to the foot of here, and this -1 should go here. So MgOH2 is my compound. MgOH2 is my compound. You see that? So is MgOH2 is soluble or not? So look here, MgOH2, Mg and OH. So Mg is right there, OH is here. So from Mg down here and going to OH, so this is the box that INSL means insoluble. So MgOH2 is insoluble. So that compound is not dissolved in water. Have you got that? Like this. So let's look another one. So I'm not looking that table here. Now I'm going to write one compound here. So PbI2. So I have a bottle here, and let's say and then the label here they write, oh, this compound is PbI2. Is it water soluble or not soluble? So I am going to look Pb and I and find that box. So let's find the Pb. Where is Pb? So Pb is right there, and I. Do I have I here? I is here. So from here, I go to I and Pb. So Pbi here. You see that? Slightly soluble, meaning that insoluble. Slightly soluble in our purpose, meaning that it's insoluble. Yeah? Oh, yeah. Oh, it's an insoluble. Yes. So Pbi here is a red. Clearly, red means it's insoluble. Yeah? Slightly soluble or insoluble in our class is called insoluble. Yeah? Have you got that? So that's a company was doing a lot of experiment, and the slight tiny bit they found by solution by using some instrument, but not with their eyes. Yeah, slightly soluble cannot be seen with our eyes. Yeah, so like that. If you got that, so So those orange button and the red button are insoluble compound. You got it? So let's look some other compound there. So um, if you practice from this table, you can easily practice the previous table. So I think this is the most easiest table to work with. So let's write one compound, Al acetate. So I'm going to write something like this: AlCS3COO3. Is this compound soluble in water or not soluble without doing experiment, right? Now we need to look the Al and CS3CO. Now find the Al and where is CS3CO? All the way down. If you look there, slightly soluble, right? Look here. So Al is right here and CS3CO is here. So I go all the way here, and from down here, slightly soluble. Slightly soluble means this compound is insoluble in water. Have you got that? So it's most easy table to work. Yeah, have you got that? So use this table for the exam. All right. So let's say here is a iron. So let's look one. Let's look the copper here. Copper and sulfide. Let's look the copper and sulfide. So copper and sulfide. So like this. So copper has a +2 charge there. So +2 charge, and this one I'm looking this one, and sulfide is this one -2 there, right? So let's go here and -2. So 2 comes there, 2 comes there. So both have 2, 2. So 2 we don't have to write there because they are same. So copper sulfide is clearly insoluble here. Copper sulfide is insoluble here. Now let's go to the periodic table there and find some other material. So here I have copper and I don't have, let's say, all answers there. I have copper, but I don't have a cobalt there. Let's go there and look the cobalt here. Do I have cobalt here? CO. I don't have any cobalt there, right? But that copper is the friend of the cobalt is the friend of the copper. So if the copper behave that way, cobalt must work that way because they are very close in the periodic table. Everybody got that? So I'm just trying to find the COS. So this compound, let's see here. I'm trying to, I know COS is insoluble by looking that table, insoluble. Now I'm going to look at COS, cobalt COS. So this compound, is this soluble or not soluble? Now I'm going to find that, where is that CO? So CO is right here. You see that? CO is very near to CU. So if CUS behave one way, COS also should behave the same way. Everybody got that? It's just like that. If one student of Chem 105 behave one way, other student must behave the same way, right? So they must come to the class at 4 o'clock and they should go out at 5:15 p.m. Make sense? So if CU and CU are sitting close in the periodic table, and if you know very well about one thing, another also should be behaving very closely with that guy. Have you got that? So if you don't see anything here in this chart, so you should be easily knowing what happens there. Now I'm going to take another example. Let's say I write Na and OH here. So Na and OH. So Na and OH. Is it soluble or not soluble? Let's practice this one. Na is +1, OH is -1. So -1 comes here. It's like that. NaOH. So look NaOH, and if you look the chart there, Na is right here, and OH is right here. So here, look here. So this is soluble, right? NaOH is soluble. Now let's go in the periodic table. So we have lithium, sodium. Do I have a potassium here? Let's click potassium. Is a potassium here? That's okay. You don't have to worry about. Do I have the rubidium here? RB here. So let's look the RB. So I don't have RB here, right? But RB is a close friend of whom? So RB is the close friend of Na. Look here. So Na is here, Rb is here. So all should be behaving same way. So if you know very well about Na, you should be easily able to predict about the Rb. Make sense? So is the RbOH is so NaOH is already soluble. We know that. Is RbOH soluble or not soluble? Should be soluble, right? Because they are in the same group. Because you know one thing very well, so all should be behaving the same way of that group. Everybody got that? And there are some exceptions. The exceptions are clearly written. Oh, this does not dissolve. So somewhere there is an exception. Let's write some of the exception. Look here. So it's lithium. So for example, is lithium phosphate soluble or not? So lithium and phosphate, Li and PO4. So Li and PO4. So these are the two things. PO4 has 3 minus. Li is a +1. You can see that. So this comes there. This comes there. So Li PO4. This 3 goes there. This compound is soluble or not soluble? Li3PO4. Look here. This is Li here, and this PO is clearly here is insoluble. So most of the compound of Li are soluble. So like LiF is soluble, LiCl is soluble, LiBr is soluble, Li is soluble, LiOH soluble. Everything is soluble with Li. Only LiPO4 is insoluble. Got it? So that's how you look this table. So if you practice, if you know how to practice this table, there are other version of this table as well. So there are some table here. There are some table here. You can just look this one. Like let's say all salts of almost. So I'm just giving the extra. This is extra, yeah. But if you have that table that I already showed, you should be able to do all kind of problem. Everybody got that? So our book present this one. Look here, who are soluble? All of the salts of this compound are soluble. Na, potassium, and ammonium. If you see this 4 material in anything, everything should be soluble. See that? So let's say I write Na plus and something else, Na plus and something else with Na, Cl, or Na Br, or Na PO. So whatever. So everything, maybe not PO4, but most of the things they are with this one are soluble. Make sense? This is another way of looking this table. And also, if you see a salt with Cl, Bri, everything is soluble. Yeah. If you see this kind of species in your salt, all are soluble. If you see salt with this F, all are soluble. If you see SO4 in salts, all are soluble. But there are some exceptions. AgCl, Ag and Cl. AgCl is not soluble. AgBr is not soluble. AgI is not soluble. Hg2Cl is not soluble. PBI is not soluble. PBBr is not soluble. That's how we look the table. Make sense? Everybody got that? So this is also the looking. So look here. Every salt is having F minus is soluble. But if you look MgF, that's not soluble. That's what it means. Yeah. MgF is not soluble. PbF is not soluble. SR, F also not soluble. Ca sitting with F is also not soluble. So if there are other things like MgCa, SR, Ba, Pb sitting with F, not soluble. But if there is a Li, Li and F is soluble, just like that. Yeah. But this table is most easy to work with. Once you know how to use this one, you can easily know how to read this one yourself. Yeah. So I strongly suggest use this one to identify which one is soluble, which one is insoluble. Yeah. Have you got that? Yes. This one? Yeah, I put that in the lecture 3. There is this table is in lecture 3. Yeah. So if you once just compare this table and try to come this table here, you can easily know which are soluble and which are insoluble in water. Yeah. Thank you, everybody. All right. Thank you, everyone. I'm ending this class.